Right. Okay. So if you can't see the slide, so hear me talking, just post something in the chat. Let me know, because I'm using a different connection right now. Okay. So last week, what we talked about in the lecture was how write accesses are handled by the cache controller in a direct mapped cache, right? So previously we talked about read accesses, then the final thing we talked about was write accesses. So when a write access comes to the cache, the controller needs to determine whether this is a hit or a miss, do the tag comparison. So in the case of a hit for write access, the block is already in the cache and we update it, and once we update it, the copy in the cache is different from the copy in the memory. So we call that block is inconsistent with the memory. So the simplest solution we discussed was to write through, that is always write to both cache and memory when a write access happens. So on a write miss, in the case the block is not in the cache, then we needed to stall the CPU just like in a read access by sending a signal to the CPU asking it to freeze, don't fetch any instructions, don't complete any pipeline stages and so on. Then read the block, send a read request to the memory to read the missing block, fetch the missing block from the memory, and you had to wait until memory responds because memory is usually a lot slower than the cache. So many cycles you have to wait until memory responds, and once you receive a response from the memory, that is the block, missing data block, you update the cache entry. Go and update the cache entry. Then we write the new data word into the cache entry. So here the write access deals with the word, whereas what we fetch from the memory is a block, right? So cache has a block. So we update the correct corresponding data word in the cache, and then we write that same data word to the memory as well. So that is the write through policy. Now, the problem we had was, what about the old block that was in the cache at that entry, which was not the one the CPU was looking for. So can we discard it? Is it okay to discard that? Yeah, it's okay because we are using the write through write policy. Whatever that old block contained in the cache was consistent with the memory because of the write through policy. We always write to the cache as well as memory at the same time. So the memory copy is up to date. So it's okay to discard the cache copy without a second thought. So because of the same reason, we can perform the writing of the data word and tag comparison at the same time, overlapping those two latencies. So if the tag comparison turns out to be a hit, then we have already done the write. It's fine. If the tag comparison turns out to be a miss, we are going to discard the data block that we written to, meaning we corrupted that data block, but we are going to discard it. So it's again fine. So we can do both operations within the same time period. There can be an overlap of the times taken for writing and tag comparison. Then write through policy, now it's very simple to implement. The cache controller is simple. The additional thing you'll be doing is sending a write request to the memory every time the cache controller receives a write request. So otherwise the controller itself becomes simple because you don't have to worry about discarding blocks. You can simply overwrite when you fetch a block from the memory, missing block from the memory. So it becomes very simple for the controller. But the problem issue on the other hand is this write through policy. It generates a lot of write traffic to the memory. So every time you get a write to the cache controller generates a write to the memory. So the bus between the cache and the memory is it can get congested with a lot of write traffic. So it's not very efficient when the program or the CPU running that program, the combination of the program, instruction set architecture, and the CPU microarchitecture generates a lot of write instructions, right? So if your program on that CPU has a lot of store word instructions that write to the memory a lot, then it's not very efficient. You're going to send all those writes to the memory. And the other thing is, every time you send a write to the memory, you have to stall the CPU. You have to wait until the memory completes the write operation, and then only you can let the CPU resume operation. So a memory access like that is about 10 to 100 CPU cycles. It can be between 10 to 100 or sometimes even more, based on various factors, based on the design of the memory, based on the communication architecture, the bus arbitration and all that. So usually around 10 to 100 CPU clock cycles. So every time you get a write, your CPU needs to be stalled for that many clock cycles, which is not very efficient. So in the CPU design stage, we talked about how we want to avoid stalls as much as possible. We tried to optimize, introduce various technique solutions to keep the pipeline running without stalling it, to minimize the number of bubbles we introduce into the pipeline. So now, if the memory is right through, if the cache is right through rather, you're making the CPU stall and waste a lot of clock cycles. So one of the solutions that we can use here is the write buffer. Write buffer is it's like a first in first out queue between the memory and your cache. So instead of sending direct requests to the memory to write, what the cache can do is put that request into the write buffer, right? So depending on the size of the buffer, you may be able to put a number of requests in the buffer, and the memory can handle these write requests in the buffer at its own speed. So as long as there are write requests in the buffer, the memory can finish the current write request and then take the next request from the buffer, the first in first out queue. So this way the CPU can carry on. This way the cache can put the write request in a write through instance, put that write request into the write buffer, and not wait until the memory responds. Just let the CPU carry on. So that takes the that can solve this stall issue every time write access happens. But the problem is, can we really keep this going? Can we keep putting everything, all the write access into the buffer? How big can the buffer be in that case? So there has to be some sort of a design decision here, some trade-off here. So the write-through policy can work decently well when the rate of write accesses generated by your CPU are slow enough for the memory to handle. Write buffer helps with bursts of write. If in your program you get a set of writes, say let's assume around 10 writes in quick succession, one after the other or very close by instructions, but then after a while, after that burst, you don't get a lot of writes after that. Then again, after a long while, you get another bursts of write. So if your program behaves like that, if your program and the CPU makes the writes in little bursts, then the write buffer solution can help, right? So the buffer can hold these writes, the sequence of bursts, 10 or so writes close by, and the memory can handle one by one, and the CPU can go on. And since there will be a gap between the end of a burst and the beginning of a next burst, so if there is a significant gap without any writes, then the memory can complete the writes in the buffer before the buffer gets filled again. Otherwise, if the CPU generates a lot of writes quite often, then no amount of buffering can help, right? Once the buffer is full, then you're back to square one. You can't let the CPU carry on. Then you have to wait until the buffer, some space in the buffer is cleared up until you can let the CPU carry on. So again, you're back to square one. You had to stall the CPU until memory completes one write access. You're only delaying that stall number of clock cycles. That's all. So that is the situation with the write buffer. It can help with small bursts of write, but if your CPU and the program generates a lot of writes, then it's still going to be problematic. You're going to have a lot of write traffic and the CPU gets stalled. So so that is the nature of the write through policy. So how can we go about and change this? I think someone at the end of last class suggested we can write blocks to the memory only when that block is thrown out of the cache or evicted from the cache, right? So that is called the write back policy. Write back policy is quite different to write through. In write through, where you write every time you get a write, you send that write to the memory as well, right? You write to the cache as well as the memory. In a write back cache controller, on a write hit, if you have the block in the cache, then you simply update the cache entry and let it be inconsistent, right? Your cache entry, let it be inconsistent. It's fine to let it be inconsistent, but we have to keep that in mind. So we have to note down that this particular block that we just wrote to is inconsistent with the memory. So that is where we use the dirty bit, right? So the status of the block we have to keep tracking. So on a write hit, you simply update the cache entry and forget about it. On a read miss, right? So there are two types of misses for read access and misses for write access. So on a read miss, when a read access comes and you have a miss, you have to go and fetch that missing block from the memory, and your existing cache block at that cache entry will be overwritten. And in the case this entry, the existing entry or the old block is dirty, or it has been written to and not sent to the memory block is not up to date, or in other words, if the cache block is inconsistent. If that is the case, you write the old block back to the memory before fetching the new block from the memory, right? So in order to do that, we have to check the dirty bit. We have to maintain the dirty bit and check it. So you write back the old block if it is dirty, then only you fetch the missing block from the memory and overwrite the old block. So in the case of a write miss, again, you write the old block back to the memory only if it is dirty, then fetch the new block and overwrite the entry and update only the cache entry. Don't update the memory, right? So this way you can avoid generating a lot of write traffic. Your write traffic will be significantly reduced between the cache and the memory, but your cache controller becomes more complex, right? You had to maintain a dirty bit along with the other arrays in the cache, tag, data, and valid bit arrays. You have to add a dirty bit array as well, and you have to check that dirty bit every time you get a miss. Right. Okay. So because of that, the write back control is more complex to implement. There's more logic behind that controller, so you have to use more hardware to implement it. But in the overall picture, it is more efficient, especially when the rate of write accesses are too fast for the memory to handle, right? So if you have a lot of write accesses coming from the CPU, the memory usually can't handle all those writes at the same speed. So if we had a write through controller, we are going to be jammed, right? We are going to be bottlenecked on the memory. In the case of a write back controller, this is going to be very efficient because we are not going to write to the memory all the time. We only update the cache, and cache is quite fast. And only when a block has to be replaced, you send that old block to the memory, and again only if that old block is dirty. So you're reducing the write traffic to the memory significantly. It becomes very efficient. Write back caches are quite efficient. And again, you can use the write buffer to send these evicted dirty blocks written back to the memory. You can send them through a write buffer. So in the event where a lot of blocks may be replaced in quick succession for certain reasons due to the nature of your program, in that case, if you have a write buffer, then those bursts of write backs to the memory can be sent through the write buffer, and the CPU doesn't have to be stalled. So the combination of write buffer along with write back cache controller will give you a very efficient cache controller, which will improve the overall performance of your entire system, including CPU. Okay, any questions? Okay, so right, let's proceed. Now, so if our cache controller is write back, right? If our cache controller uses the write back write policy, then the structure of our direct map cache has to look something like this. So in addition to the data tag and valid bit arrays, now we have this dirty bit array as well, right? So every time you make a write to a block in the cache, that block has to be marked as dirty, meaning inconsistent with the memory. So the most up-to-date copy is in the cache, not in the memory. So that is the idea of the dirty bit. So what happens when the controller ends up with a miss? If you have a miss, then the cache controller will have to consider this dirty block before replacing that cache entry with the new block. So that is the idea, that is the concept behind the write back policy. That is this new added array into your cache structure. Right. Now we are going to talk a little bit about cache performance before we move on to other technical content. So the average access time for a cache, we have defined this earlier as well. TA average or TAVG can be defined as equal to hit latency plus miss rate into miss penalty, right? 1 minus hit rate is miss rate, right? The portion of misses in your program, or the fraction of misses. 1 minus HR is that, so HR has to be a fraction, given as a fraction. So your average access time is hit latency has to be there, right? So the time to determine a hit is there always. For in addition to that, for the accesses that are going to be misses, for the fraction of accesses that are going to be misses, you have to apply the miss penalty as well. Miss penalty is the time you take to fetch a missing block from the memory. So the average access time can be expressed like this. We had a look at this early on as well. So the time values variables in this equation, that is the average access time, hit latency, and miss penalty, you can express them as either absolute time, nanoseconds, picoseconds, or in clock cycles. So as long as you are using the same unit for all the terms here, you can you can use either time, absolute time, or clock cycles. Then let's make some assumptions for a certain scenario. Let's assume our miss penalty is 20 CPU cycles, right? That is, if we have a miss in the cache, we have to go and fetch that missing block from the memory. Fetching the block from the memory process takes 20 CPU cycles, okay? Then for the program that we are assuming with the CPU, ISA and all that, the hit rate in this cache, in a certain cache we are talking about, is 95%. That is, 95% of the accesses are going to be hits in the cache, right? So that depends on a lot of things. That depends on the cache as well as your instruction set, how the pattern of memory accesses generated by your program running on the CPU. So 95% of those accesses are going to be hits. If we express that as a fraction, 0.95. Then the hit latency, the time to determine a hit is one CPU cycle, right? So within a single CPU cycle, you can determine whether this access is a hit or miss. So in the case of a hit, your cache can supply the data within one CPU cycle. So the CPU clock period is 1 nanosecond. That is, the clock frequency is 1 gigahertz, right? So these are the assumptions that we are making. So what is the average access time here? Using the equation we have at the top of the slide, average access time is 1 plus, that is hit latency, plus 1 minus hit rate is 1 minus 0.95, and 20 miss penalty, 20 cycles, right? So we are using cycles as the time measure here. So T average access time for this cache is 2 clock cycles, right? On average, every access will take 2 clock cycles, but if we look at individual accesses, hits will take 1 cycle, misses will take that 1 cycle plus 20 cycles for handling the miss. So 21 cycles, right? So if you average them out, you get two cycles on average per memory access, per cache access. That is 2 nanoseconds, right? Since the clock period is 1 nanosecond. Now, can you do this calculation? If your hit rate goes up to 99.9, if we can, with some techniques, improve the hit rate up to 99.9% from 95. That is, the fraction is 0.999. What is T average? Can you quickly calculate and tell me? So I have one answer sent to me privately. That is, you can reply to everyone so everyone can see. It's 1.02 nanoseconds. Yes, 1.02 nanoseconds. So you only have to replace this hit rate 0.95 with 0.99, and everything else is the same. So you end up with 1.02 clock cycles, 1 nanoseconds, closer to 1 nanosecond, right? So since 1 cycle is 1 nanosecond. So as you can see, if we can do some improvement to the hit rate if we can tune our cache to get a better hit rate. Now keep in mind that hit rate is dependent also on your program, also on your ISA, also on your CPU, and right, everything above. So if you can somehow improve the hit rate, get better hits, right, get large amount of hits, you can improve this average access time really significantly. So from 2 cycles average closer to 1 cycle average is a really big improvement, right? So so yeah, keep that idea in mind. We'll be discussing that further. Right, now here's another question for you to work on. Assume a program. We are running a program on a CPU. 36% of the instructions in this program are load and store instructions, right? So out of all the instructions in the program, 36% of them are loads and stores. The remainder 64% are non-load store, non-memory instructions. So the CPI, the cycles per instruction of the processor is 2 if we can assume the caches are ideal. That is 100% of the accesses are going to be hits in the cache. That means the CPU doesn't have to be stalled at all, right? Due to any cache misses. So no stalls due to cache misses. That is the idea of ideal caches, 100% hits. If we can get 100% hits, the CPI or cycles per instruction of the processor is 2. And that is every instruction is, or rather on average, every instruction is consuming 2 clock cycles in the CPU. Okay, assuming ideal caches. In reality, we don't have ideal caches. There are some accesses are going to be misses. In reality, the actual instruction and data caches have 2% and 4% miss rates respectively. Instruction cache miss rate for this program on this CPU is 2%, and we have a data cache which has a miss rate of 4 for this program on this CPU, right? Then the read and write miss penalties are 100 CPU cycles each. So for a read miss or write miss, the miss penalty is 100 CPU cycles. And these caches, instruction cache and data cache, take 1 CPU cycle to determine the hit status. That is, to determine your hit, that's the hit latency. Hit latency is 1 CPU cycle. So, right, here are the questions. First one is, what is the actual CPI of the processor, right? So when we have these real caches connected to our CPU, what is the actual CPI? The ideal CPI is 2 that we have been told. When we have the real caches connected, what is the actual CPI? Then how much faster would your processor run if these ideal caches are indeed available, right? If with some magic, if we can have ideal caches, then compared to your real caches, how much faster your CPU will run? What is the speed up, right? The speed up ratio. Third question, if you have no caches at all, if you had to connect to the memory directly without having caches, how slower would your processor work compared to having the real caches, right? Okay, so those are the 3 questions. So shall we have a look at the first question? Can you do this calculation? What is the actual CPI of the processor? Ideal CPI is 2 CPU cycles. With the real caches, let me actually walk you through this. Assume your program has I instructions in total, right? We don't know the number of instructions. We are only being told that 36% of the instructions are loads and stores. So assume that we have I instructions in total, I number of instructions. Then we can state that the cycles CPU will be stalled due to instruction cache misses, like this, right? So you have I instructions, 2% of those are going to be misses in the instruction cache. And when you have a miss, your CPU is going to be stored. So 2% of those instructions are going to be misses. For each of the misses, you are going to stall the CPU for 100 clock cycles until the missing data is fetched from the memory, right? So 2 times I clock cycles are going to be stalls due to instruction cache misses, right? So similarly, because of data cache misses, the number of stalls your CPU will take is, you take the total number of instructions, that is I, 36% of those instructions are going to be misses in the, no, sorry, 36% of those instructions are going to be loads and stores, right? 36% are memory related instructions, loading from the data memory or store into the data memory. Out of that 36%, 4% are going to be misses in the data cache. That is the miss rate for the data cache. And for each of those data cache misses, you have to store the CPU for 100 clock cycles, right? So the number of cycles told due to data cache misses is going to be 1.44 I, right? So 2 I cycles are going to be stalled due to instruction cache misses, and 1.44 I cycles due to data cache misses. So the total number of stall cycles is 3.44 I, where I is the total number of instructions. Then the actual CPI, you can calculate the ideal CPI plus the cycles you are going to, on average, how many cycles the CPU will be stalled due to cache misses. 3.44 I stalls total for I instructions. So for one instruction, you can divide it by I, and 3.44 per instruction, 3.44 cycles are going to be stored. So actual CPI is 2 plus that, which is 5.44 cycles, right, per instruction. On average, our CPU will spend 5.44 clock cycles, considering we use these real caches, right? So compared to ideal caches, this looks quite slow, right? So that is our second question. How much faster would our processor work if we had these magic caches, ideal, perfect caches, where you don't have any misses at all the accesses are hits, right? So the speed up is 5.44 divided by 2, which is 2.72, right? So if you have these magic caches, you can speed up your processor by a factor of 2.7 times, 2.72 times, right? How much slower your CPU would work if there are no caches at all, right? So we have real caches, and our CPI for that is 5.44. And if we don't have caches at all, what is the slowdown due to having no caches at all? So the CPI for no caches, you can calculate. Ideal CPI is 2. Then per instruction, if you have no caches at all, 100% of your access are going, you can assume as misses, meaning you have to go to the memory, right? So for every time you go to memory, you spend 100 clock cycles. So for each and every instruction, you spend 100 clock cycles fetching from the memory that instruction. And 36% of those instructions are going to be loads and stores, and for those loads and stores, you spend 100 clock cycles, right? So for the fraction of instructions that are loads and stores, 36%, you are spending 100 clock cycles. So 0.36 times 100. So that is 36 cycles, right? Store cycles due to those load store instructions. Data memory stores. So this is instruction memory stores. And per instruction, that number of stores, you divide the total by I. And the result is 138, which is a massive number if you don't have caches at all. If you don't have caches at all, your CPI is 138 compared to 5.44 if we have this real caches where you have 2% and 4% miss rates. So your CPU is going to slow down by a factor of 25.37 if you don't have these caches, even the real caches, right? Okay. Now, with that performance computations in mind, next thing we are going to talk about is how to improve cache performance. What can we do to improve cache performance? And when we want to improve cache performance, if we take that equation, the average cache access time, average memory access time rather, because CPU thinks cache is the memory, then you have to improve these factors, hit rate or hit latency or miss penalty, right? Those are the things that you have to try and improve to get better performance, right? Hit rate, hit latency, and miss penalty. So first thing is, let's talk about hit rate. Can you come up with some suggestions about how to improve the hit rate of the cache? Let's assume that our program and CPU, ISA, everything is fixed, right? So we can't go and change anything from the cache side. What improvements can we do to get a better hit rate? Can you suggest something? Any ideas? Any suggestions? Shamit says larger cache size. Yes, very good. So how can larger cache size help? Because we have been talking about the direct map cache size. So how can larger cache size help improve the hit rate? It's correct. Larger cache size is correct. Bigger caches give you better hit rate. How exactly? Can hold more things. Locality improves. Yes. So in our direct map cache structure, if you remember, for there can be multiple memory blocks that map to the same cache block, right? With the same index. So if you have a larger number of cache blocks, if you have more entries in the cache itself, then that means your index field, the size of your index field also increases, meaning you have more entries in the cache and lesser number of mappings to a single cache entry, right? So a conflict occurring, the chance of a conflict occurring is less now with a larger cache, right? So say in our previous examples, when two addresses have the same index and one is already in the cache and you are referring, the CPU requests the other address, then the older one has to be evicted because the new one has to replace it. So if we have more entries in the cache, then the likelihood of the next, the second address being mapped to a different cache entry is more higher because the index field size is bigger and the chance of having a different index pattern is more, right? So that is how exactly you get better hit rate with a larger cache. So you're serving, you're exploiting locality more with bigger cache, right? The temporal locality is better exploited with a bigger cache. But then on the flip side, when you have a bigger cache, you have to use more chip area to have that bigger cache. So as if you remember, this SRAM technology is very expensive. So larger caches, meaning your cost is also going to be very high, right? Remember, some $2,000 odd per gigabyte. We are not going to have gigabyte size caches, but still your cost is going to be really big if you try to keep improving the cache size. So there's a trade-off, right? Cost versus performance. Okay, so bigger cache size is it's a correct answer, right? So improve the hit rate, you can increase the cache size, or more entries in the cache, more blocks in the cache. Okay, so let's try to recall this direct mapped thing again, direct map concept again. So your different data blocks on memory can map to the same index, like what we saw in that slide previously, right? So two different addresses with the same index, right? So if you have more indices, right? If you have more cache entries or cache blocks in the in this cache, then you need more bits in the index field to address or refer to those entries. So this index field will widen, and when the index field widens, you have better chance at having different different indices, having mapped to different indices rather than the same index, right? So that is the idea behind increasing the size of the cache. Now, having this same example here, let's say in this particular example, now the old axis is this one at the top, and the new axis is this one at the bottom, right? They have the same index, and well, the older one is going to be evicted from the cache when the new one is referred to by, new one is referenced by the CPU, right? When the CPU wants to access the new address, the older block is going to be replaced. But assume if you have an empty block here somewhere else in the cache. So having to throw out this old entry while there is an empty block here is not very beneficial, considering our locality principles, right? The locality, say temporal locality, says the accesses that are referenced now are more likely to be accessed again soon, right? That is the temporal principle of temporal locality. So this old block was in the cache because it was referenced quite recently, and we have an empty block here, or an invalid block, some useless data block here, which you can replace, but the direct map concept tells the new block also has to map to that place, right? Otherwise we can't find it. So we need some sort of a different mechanism to handle this. So right, so if this evicted block now, the one that is thrown out, if it is accessed again, temporal locality says there's a good likelihood that block already in the cache is likely to be accessed again. Then we are having a miss. Then the hit rate is actually affected, right? It goes down. We have thrown out an entry which has a likelihood of being accessed again. So hit rate is suffering because of that that old block being thrown away or evicted. So what if we ditch this direct map concept and try to come up with something else? So imagine that let's get rid of this location in the cache or the index concept, right? So the index concept is there because of the direct map concept. You need the index to identify where a given block is in the cache, right? Otherwise you had to search the cache. So that is the problem that we had. So let's just ditch this index, right? So if we drop the concept where a memory block maps to a particular location in the cache, then you don't need the index. You can drop that. Location mapping concept is gone, index is gone, and there will be no index field that an incoming address block address will have, right? We don't have an index. Everything you can consider as the tag. So this multiple block mapping to the having to map to the same address because of the same index, that idea is also gone out of the window, right? So we are ditching all these things. Okay. So if we get rid of all that, what we have, we call is a fully associative cache. That means a block can be mapped anywhere, right? There is no particular mapping for a given block address in the cache. There's no mapping saying, okay, this block address has to be in that particular place, that particular entry. But there's nothing. A block can be anywhere in the cache. So everything else is still the same, right? So we have a block size of 8 bytes as we assumed previously, and the cache can still hold 8 blocks. And we don't have an index field anymore with our addresses. Everything is tag plus offset. Offset is within the block what is the word or what is the byte you're referring. Otherwise, the rest of that is tag. So since our block is 8 bytes wide, we need 3 bits offset to refer to individual bytes, or 1 bit to refer to individual words. There are 2 words in the block, right? Okay. Now, where can this address be if we fetch this block from the memory from that address? Where can that be? We don't have this mod by 8% and mapping to a particular entry in the cache anymore, right? So no index like this. So where can it be? Can be anywhere, right? So how can we find this block now? We introduced the direct map concept with the index field in order to find the block when the CPU need it, right? Otherwise, you had to do a sequential search, and we don't want to do sequential search. It's not going to be efficient, right? Every time you get an access, you spend a number of clock cycles looking through your cache, and in the worst case, if your entry happens to be at the very end of the cache and you start from the bottom, you spend that many clock cycles trying to look for this. So yeah, sequential search is a no, we don't like it. Then parallel search, right? So just like with anything in hardware, you can improve the performance by doing things in parallel, by having more hardware, right? So to do that, how do we do this? You need one comparator per entry, right? Do a parallel tag comparison. Remember the tag comparison we did with the direct mapped cache? We find the correct entry using the index field and then compare the stored tag with the incoming address tag. Now, since we don't have that index concept, we have to compare the incoming address tag with each and every entry's stored tag at the same time. So parallel tag comparison needs parallel tag comparison hardware, right? You need to duplicate the comparator hardware that we discussed in the previous class to perform this parallel tag comparison. So it's practical only for small number of entries. If you have a certain, say a smaller number of entries, like 8 is a very small number here, it's a small example, so 16, 32, 64, a smaller number of entries in the cache, then but as you keep increasing the number of entries in the cache, then you have to keep adding more and more comparators, parallel logic, which will add more and more wires, increase the length of those wires when you have to place everything in the chip, which will going to add more delays when determining your hit status, right? Which we don't really like. So yeah, so for a small number of cache entries, this is fine. So yeah, now a question we can have here is where to place a new block now. We don't have a mapping from memory addresses to cache entries. We dropped that. So where to place a new block? How can we place a new block? Now we fetch something from the memory. Where to put it? We know that we can put it anywhere, right? We can put it anywhere, but the hardware has to do it. No, hardware has to put it somewhere. So what is the policy behind it? What is the policy we use to place a new block? So what we'll have to do is we have to add some hardware circuitry to find the first available invalid entry, find some invalid entry in the cache which you can put it, right? So rather than throwing out something that is existing there, if you have an invalid entry, yeah, that is the best place to put. If you have multiple invalid entries, you have to pick one. So we had to have some logic behind it. So the straightforward or the intuitive one is go through the cache, find the first one with the valid bit cleared or invalid entry. So it will necessarily have to be done using sequential logic, right? So it's going to consume more time. So yeah, unfortunately it will be affected, but there's no way around it. What happens if there are no invalid entries? If all the entries in the cache are valid, then we have to throw something out of the cache, right? Earlier in the direct map version, there is a particular memory block, a cache and location for every memory block. If there is something already there, you have to evict it, right? Then the write back, write through policies, all those things are there. So now with this fully associative cache architecture, we have to find a cache entry to evict again, right? So what is the cache entry that we should throw out? What is the ideal policy behind it? Can someone tell me? How can we decide on a cache entry to throw out or evict? What is the policy that we can use for this? All the cache entries are valid. We have to pick one to throw out in order to make some space for a new block. Any ideas? Using the principles of locality. What should stay in the cache and what should be thrown out? Any idea? That is where this concept of replacement policy comes into the picture, right? So ideally, if we want to exploit the temporal locality principle 100%, then we have to have a policy like least recently used block is the one that should be replaced, right? So our cache is full and we have to know which one was least recently used, right? So that is the ideal candidate to be thrown out of the cache to still like exploit the temporal locality principle the best, right? So temporal locality says recently used pieces of data are likely to be used again. So the most recently or more recently used ones are more likely to be used again. So if we stick with that principle, then the least recently used one is the one to be thrown out. But designing a cache controller to do that is a very complex, difficult thing. We need to keep track of when each cache entry was used, each cache block was last used, right? So the last use of each cache entry, we have to store in the cache. We have to timestamp every time you you reference a piece of data. You see if you ask for a piece of reads or write to a particular cache block, every time you have to update this. Some particular hardware needs to update certain time stamping mechanism um, in order to know which ones are more recently used and which one is the least recently used. And to do this, to implement this exactly like that, you are going to have a very complex piece of hardware, and it's not often done in practice. Right? In real practical caches, the LRU replacement policy is not always used because it's really complicated, and it's going to make the cache controller very complex and slow, so and costly. Hardware wise, it's going to make it very costly. So um, rather than the ideal LRU policy, most caches use this pseudo LRU policy, which is not you are not time stamping everything per se, but you can come up with some simpler mechanisms which is closer to LRU but not exactly LRU. That is, there is a chance that you might be throwing out something else other than the least recently used block, but say 90% of the time or 99% of the time, you can you're likely to go to this likely to throw out the least recently used block. So some simplifications to the LRU policy can be done. So pseudo LRU implementations are there, which are in practice used. Simpler controllers, which 100% of the time you can't pick the least recently used one, but for a significantly high portion or fraction of the time you can pick it. So PLRU are that. Then first in first out is a very simple alternative. It's not exactly the least recently used one, but first into the cache, even though you might be that block might have been referenced later. First in, first out, right? So you just need to update the tag only when the cache block is updated with a new block, right? When a new block is fetched from the memory, you update a particular location or flag in the cache, but not every time that is referenced. So first in first out is a very much simple implementation. It's a simpler cache controller, but the likelihood of picking the least recently used cache block is lesser compared to PLRU. But because the controller is very simple in things like these embedded computing systems, embedded computers, when you add a cache memory, usually you go for FIFO policy as the replacement policy, because it makes the controller simpler, less hardware, less costly, less power consumption, and all that are coming with that. So a lot of different design decisions behind these choices, right? So ideal one is least recently used. If you want the best performance, meaning if you don't if you don't want to lose any locality based time improvements, then LRU is there. Or PLRU if you want to get a good performance with a relatively simpler controller, less power, less costly hardware. Or if you want a very cheap hardware with a little bit of, say, less performance, 5.4 is a good option. So those are the practically things that we practically see, and first one is actually ideal, but not seen in practice a lot. Okay, any questions at this point? Anything you want to ask? Okay, I'll take that as a no. So let's go ahead. Right, so with this fully associative cache concept, what do we like? High utilization of cache space, right? So we can have a better hit rate because we are throwing out, there's a good chance of keeping cache blocks in the memory compared to the direct mapped implementation, right? So better utilization of cache space. In the direct mapped implementation, the utilization of cache space is not that good, because you might be throwing things out of the cache while there are empty spaces in the cache at the same time. So high utilization of space is something good, which will give us better hit rate, and you can choose the replacement policy as needed based on your application, based on your what sort of a computing system you're designing. So if you want really high performance, you go for things like PLRU. If you go for low cost and low power, you go for replacement policies like first in, first out, right? Simpler controller, compromising some performance. What do we not like with fully associative caches compared to direct map? That is, the block placement is slow, right? We have to go and search for an invalid entry. So every time you fetch a new block from the memory, you are spending more time. That is, your miss penalty is going to increase, right? You have to spend more time to find the place to put the newly incoming block from the memory. You have to search for an invalid entry. Then your power consumption is likely to be higher compared to direct mapped, because displacement circuitry is going to consume more power, right? More hardware is going to always consume more power anyway. So the cost is also going to increase due to all this added hardware, right? You need added hardware for block placement, added hardware for block replacement, right? Replacement policy to support that. You need more hardware. You need to store more information with the cache entries, and more hardware to use that information and make decisions, and parallel tag compare in order to determine hits, right? So, and certain other things as well. So fully associative caches, the cost is going to be high. The cache controller is going to be bigger, more complex, consume more power, and the block placement can be slow. In the case of a miss, the miss penalty can be higher compared to a direct mapped cache. So that is what we don't like, right? So we had to consider all these factors when we decide whether to use a direct map cache or a fully associative cache in our computing system, right? Okay. Now, in between these fully associative and direct map, we have this concept of set associative caches, right? So this has both direct mapped as well as fully associative techniques in the same cache. So this is, if you look at an array like this, or rather cache structure like this, you have data array, tag array, and valid bit array. You can have the dirty bit array depending on your write policy. Let's just ignore that for the moment. then you need indices to access these individually, right? So that is the direct map cache structure. Index bit is actually not stored, but you use these indices to refer to these different entries, right? So what if we add another copy of this set of arrays? You have valid tag and data. You add another set of those arrays, valid tag and data for the same entries, so same indices, right? You essentially double the size of the cache, right? Earlier we had 8 blocks, now we have 16 blocks which we can put in the cache. So each index now refer to two different blocks, two different entries, right? So we call this a two-way set, right? One entry is now a two-way set. We refer to that as a two-way set, and we refer to this particular cache structure as two-way set associative cache, right? This is not exactly direct map, not exactly fully associative, but somewhere in between, right? So if we assume the same block size, 8 bytes, this particular structure that we are looking at can hold 16 blocks, right? The original direct map structure we looked at can hold 8. This can hold double that many. At each index, you can store two different data blocks along with the corresponding tags and the valid bits, right? So one index refers to a two-way set now. Earlier in the direct mapped architecture or direct map structure, one index referred to one data block, right? So the index is for a block. So sometimes we refer to that as a block index cache, block index. Now we refer to this index field of our incoming address as the set index because it is referring to one set of data blocks, right? You can have two data blocks in one set in this particular. If you want, you can have more. If you add more sets of these arrays, you can have more. Usually you don't have, sometimes you have three-way, but usually you have in powers of 2, right? Like two-way associative or four-way associative caches or 8-way associative caches. So in one set, you have that many data blocks, different data blocks, right? So the index in this case is the set number rather than the block number, and your incoming address has to be very similarly looked at, just like to very similar to direct mapped caches, right? You have the tag, you have the index, and you have the offset. Offset refers to a particular word or byte inside the block, right? So that is that, and the index refers to this set. Now it doesn't refer to one particular block, it refers to a set of blocks. So we call that, sometimes we call that the set index in a set associative cache, and the remainder of the address is the tag, and you have to store the tag along with the corresponding data blocks, right? Okay, now assume that you're getting an incoming address like this address. You divide into the portions tag, index, and offset, right? So let's assume that this is a read access. What we are seeing is a read access to this two-way set associative cache. Now we are going to have a look at how this read access is handled by the cache controller, right? So this access is a read, so you have to you will receive the read control signal along with the address, right? If this was a write, you will receive a piece of data to be written as well, but read access will only get the address as well as the read control signal, right? Now what is the first thing, since everything happens in parallel, what is the most important thing that we should do? We should first find the correct cache set that this address is referring to, right? So for that, we use the index field, use a demultiplexer to point us to the correct entry, right? We have 8 entries using this 3-bit index field. Using a demultiplexer, we will we will get a pointer to the correct cache entry. Then we can extract the tags, the 2 tags in that entry at the same time in parallel, right? This is very similar to how this was done in fully associative cache, even though we didn't look at the diagram for that. But in this case, we have to have 2 parallel comparators to compare the 2 stored tags in that set with the incoming tag, right? So you extract the 2 stored tags, send them to the 2 comparator circuits, and send the tag portion of the incoming address to those comparator circuits. They will compare the incoming tag with each of the stored tags, right? So you will get a matching status here. 1 if the tag is matching, 0 is the tag is not matching. So can there be multiple tag matches? What do you think? Can there be multiple tag matches? Can both of these tags match or only one? What do you think? There seem to be a lot less responses today. Okay, only one, Dinidu. Right, yeah, only one tag can match because the tag specifies the exact block that this is referring to, and there cannot be 2 different blocks with the same index and the same tag, right? So if you have the same index and the same tags, that is the same block, right? So you can only have one of them, right? Good. Okay, so well, the tag comparison is done. What is the other thing then? You have to check the valid bit as well, right? So valid bit tells whether this entry is valid or not. So again, we have to have duplicate hardware to do the valid bit matching. So we extract the stored valid bits from the cache set and use an AND gate, just like we did in the previous implementation, direct map. Then actually send that valid bit to the AND gate along with the output of the corresponding comparator. And you can get a hit status for each individual, we call it way, right? So remember, we call it 2-way set. This set, we call it a 2-way set. We say that a data block can be stored in 2 different ways within this set. So this is way 1, this is way 0, or the other way 0, way 1. So for each of these ways a data block can be stored, you can get a hit status here, hit 0 and hit 1. So hit 0 saying this is the this is a hit or a miss in way 0, right? So this is way 0, this set is way 1. So in way 0, this signal will tell whether you have a hit or not. In way 1, this signal will tell whether you have a hit or not. So only one of them can be true and can be set high at a given instance, right? You can't have both of them going high. Right, okay. So that's the hit status for individual ways, and then we have to aggregate that signal, those two signals, using an OR gate. If one of them are true, then we have a hit. If both of them are 0, then that means none of the tags are matching. None of these two blocks are the one that the CPU is looking for, right? So that is a miss in that case. If you have at least, well, if you have exactly one here matching, then we have a hit. You can't have more than one matching, but you can have all of them not matching. In that case, we have a miss, right? So that is the hit, misdetermining hardware. So we have parallel comparators, and we have to aggregate through another OR gate the output signals of those AND gates, right? So more complex hardware. Right, now what about the data blocks? We have to extract the data block now. So since we know the index at the start, we can extract the data block while performing the tag comparison. And we have two different data blocks now, right? We have two different data blocks. How do we know which one is the appropriate one? If there is one, that is. Can you tell me? How do we know which one is the appropriate one? If there is an appropriate one. Last bit of tag. Will that help? How can the last bit of tag help? Hit 1. Okay. That is a good suggestion. If hit 1 is 1, then we know we have to take that data block from the way 1, right? Hit status of two comparators. Yes, exactly. You need both hit status. You can't, well, in this particular instance, you might be able to use one, but if you have more ways, right? If you have more comparators, then you really can't use only one hit status. You have to use all of them. So hit status of each and every comparator plus this AND gate you have to use in order to figure out the data block, which data block we are referring to, right? So what we had to do is send these hit signals, hit 0 and hit 1, through an encoder and generate the corresponding select signal for this multiplexer to select the data block, right? So since we only have two ways in this cache, you use the two hit signals to generate a single bit select signal, right? So 2 to 1 encoder. If you have four ways, right? If you have two extra sets of arrays here, then you will have a 4 to 2 encoder, right? 4 inputs, 2 bit output encoder, which will select one out of the 4 data blocks from the 4 ways. So you have to have an encoder circuitry now based on these hit 0 and hit 1 signals, and then select the send that as a select signal for the multiplexer. Then you can extract the correct data block. Then just like we did in the direct map cache, from that data block there are multiple data words, and you have to select the appropriate data word based on the incoming address, and for that we use the offset signal. So in our example, if we have two words in a block, then you have to use the most significant bit of the offset field as the select signal here to select one out of these two. If you have more than two data words in a block, then you need to use multiple significant bits of the offsets signal, right, to select the correct data word, and then you can send. Now, it should be noted that your delay is much higher compared to the direct mapped implementation. You had to wait until the hit signal is, these hit signals are stable, right? You update these hit signals and they stabilize. Only after that, the encoder output can be stabilized and you can select the appropriate data block, right? So your data block selection from each and every way, different way, depends on the output of the comparator tag comparison circuitry. So you have to, your delay needs to be increased. The hit latency time is increased now. It has to wait until this is done for that to be done, and then only you can extract and send the data word, right? The up-to-date data word will be available at the output here after a longer delay, right? So hit latency is now increased a lot. So the fully associative is very similar to this, only you didn't have the index field, right? We ditched the index field entirely. So there'll be multiple tag comparisons, multiple ways here. So all those things, all these things here, tag comparison, data block extraction, figuring out which block is the appropriate one, then figuring out which word is the appropriate one. All those things are there other than this index. You don't have an index field, and consequently you don't have a demultiplexer to find the correct entry. There will be only one entry and multiple ways in there. So that is just to give you an idea about the fully associative implementation, right? Okay, so this is the set associative cache implementation for a read access. We will not go and do look at the write access. You can imagine how the write access happens here. So very similar to the same setup. You have to do the parallel tag comparisons and determine intermediate hit status and the final hit status, and then instead of these instead of these multiplexers, you need to use demultiplexers to send the data word or the data block to the correct way in the cache, the matching way in the cache. Right. So, okay. Now, so this concept of set associative caches gives us a new term, associativity, right? So like I said, in a set associative cache, you can have two-way sets or four-way sets or eight-way sets, usually in powers of two, but there are certain designs, the number of ways you have in a set is not a power of two as well, but usually it's a power of two. So you have a new term, associativity, right? So let's look at how that affects the organization of an 8-block cache as an example, right? So our if our 8-block cache is designed as a two-way set associative cache, the structure or the organization is going to look something like this, right? So you have two different ways or sets of arrays, right? So at each entry, at each index, there are two ways you can store a data block, right? So you have space for 8 data blocks in this two-way set associative structure. Now, the same space can be organized as a four-way set associative cache as well, right? You still have 8 block space, but now each index can store 4 different blocks in 4 different ways, right? There are 4 different ways, 4 different sets of arrays. Each index can store 4 different data blocks, and you have 2 such entries here, right? Index 0 and index 1. Earlier, With the two-way set associative, you had 4 indices. So the index field was 2 bits wide. Here, 4-way set associative with the same cache size is you have only 2 different indices. So you only have 1 bit for the index field, right? That is a 4-way set associative. If we arrange the same thing as an 8-way set associative cache, it becomes a fully associative cache. You don't have the index field anymore. You only have 1 index. So there's no point in using a bit field from the incoming address. There is only 1 entry that you have to refer to anyway, right? So we have dropped the index entirely. No index field from the incoming address. There's only 1 entry in the cache, and in that entry, there are 8 different ways, right? So that is the fully associative implementation. In this particular instance, 8-way set associative for an 8-block cache is the fully associative implementation, right? So you need to have 8 copies of the tag comparison hardware and data extraction and data writing hardware, right? Okay. So on the opposite end, we can have a one-way set associative cache where at each entry you have 1 way of storing data, right? So that is the direct mapped implementation that we first talked about, right? So you can see the spectrum of different implementations for an 8-block cache. Direct mapped is the same as one-way set associative, right? So you have 8 different indices, 8 different entries. At each entry, only 1 place, 1 way to store data, piece of data. Here, 4 different entries. At each entry, 2 different ways to store the data. 4 ways set associative, 2 different entries, and 4 different ways to store the data at each entry, and then the fully associative version. So 8-block cache can be arranged in 4 different ways like this, and 4 different values for associativity. Associativity is 1 here, associativity is 2 here, associativity is 4 here, and associativity is 8 here, and we call this fully associative, right? So okay, any questions? Right. So since we can have different organizations like this, say if you're going to have an 8-block cache, if you decide the size is going to be 8 blocks, then we can implement the cache in multiple different organizations like this. So which one is the best? It depends on a lot of things, a lot of different factors, right? It depends on your program, can depend on the CPU microarchitecture, can depend on what sort of a performance improvement you want. Do you want less power consumption? Do you want better performance? All those different design decisions are coming into the picture, right? Which one is the best? But since we are talking about improving the hit rate, let's see which one gives us the best hit rate, or rather how the hit rate change with the associativity, right? So let's take a small example for that. We are going to compare 4-block caches, right? A cache with 4 different blocks. Cache can store, which can store 4 different blocks, right? So half size compared to the previous example. So in this example, block size is 1 word, right? 1 block is 1 word. Okay, 1 word is a block also. Block size and word is the same now. Then word size is 4 bytes. 1 word is 4 bytes wide, and 1 block is also 4 bytes wide, and 8-bit incoming addresses, right? Address is 8 bits wide. Okay, so this is our example. Now the 4-block cache can be organized in 3 different ways like this. One is direct mapped, 4 blocks in at 4 different entries. using 4 different indices, right? So this is the direct mapped implementation for a 4-block cache. You have to store the tag and valid bit, and there'll be 4 different entries. So you need 2 bits to identify individual entries, 2 bits from the incoming address, which we will use as index field. Then the two-way set associative implementation, the 4 blocks can be organized like this: 2 entries with 2 blocks in each of them. So you need 1 bit to identify these two different entries, right? Then the third way is 4-way set associative, in this case fully associative implementation, right? For 4 blocks, if you have all 4 blocks in the same entry, that is the fully associative implementation, all 4 blocks in the same set. You don't have an index field in that case, right? You only have 1 entry in the cache. So note that at the very beginning, our tag fields are all set to 0, all cleared. Valid bit is set to 0 in all the entries, and yeah, so in all 3 different cache organizations, valid bit is set to 0 for each block, and the tag bits are set to 0 for each block. And the data, we don't know, it can be 0, it can be something else, we don't know, right? We don't know because these are not valid data, right? So don't care. Note that the tag size is different in the direct mapped implementation. Your tag size is 4 bits, right? Tag size is 4 bits, index size is 2 bits. So 8-bit addresses, we have 2 bits remaining. That is the offset to identify individual bytes within a word, right? 2 bits to the offset field, then 2 bits for the index field, and the remaining 4 bits for the tag field. In the two-way set associative implementation, offset is the same 2 bits, index is 1, so tag size is higher now. Tag is 5 bits. In the fully associative implementation, tag is 6 bits with no bits for the index, right? Offset is still the same 2 bits. Right, now let's go through some memory accesses. So the first memory access is this one. We have an 8-bit address here, 0, 0, 0, 0, 0, 0, and we don't know the offset bits, the exact bits we are using to refer to a particular byte. We don't know, and we don't care, right? We don't care about inside the word what is happening. So the memory is the CPU is asking for a word, and that is the address, right? So this the part in black is the block address, and for different cache implementations, the tag and index sizes of these are different, right? So we have the block address 0 here. So if we take the direct mapped implementation first, it is referring to index 0, right? 2 bits are used as the index, the 2 least significant bits of the block address, and index 0 is here, right? So is this a hit or a miss? Is this access a hit or a miss? Imagine these are reads, okay? These are reads, only reads. We are looking at only we'll be only looking at reads. Will this be a hit or a miss in this direct mapped cache? It's going to be a miss, right? Yes, exactly. It's going to be a miss because of what? Valid bit is 0, right? That is correct. Very good. Valid bit is 0. So this is going to be a miss because the valid bit is 0. Note that the tag is actually matching, right? So that is why we need the valid bit. Tag is matching, but valid bit is 0. So this at the very beginning, the data doesn't mean anything to us, right? So it's some garbage or random data. So the valid bit is cleared. So this is going to be a miss in the direct mapped implementation, it's going to be a miss. What about the two-way set associative implementation? You use the single least significant bit from the block address to refer to one of the entries. So 0 refers to the entry 0. And is it a hit or a miss? You will do that parallel tag comparison and all that. And what will be the outcome? It's going to be a miss again, right? Because valid bit is 0. Again, for both the ways in this cache, the valid bit is 0. Way 1, valid bit is 0. Way 0, valid bit is 0. So the hit status is going to be actually miss. So what about the direct map? There is no need to use an index. You refer to this single entry directly, and perform four parallel tag comparisons and valid bit comparisons. All the valid bits are 0, so you get a miss, right? So something to note here is that when an address is referenced by the CPU for the first time, it's going to be a miss anyway, right? Your cache is not going to have it the first time an address is referenced. Only when that address is referenced again afterwards, you can have that address in the cache, the block in the cache. So these first time misses, when a program and cache and the system, entire system starts, the initial misses for the addresses, they are called cold misses, C-O-L-D, cold misses. From a cold start, the first time addresses are referenced, they are going to be misses anyway. Those type of misses are called cold misses. Then the other way that you can have a miss is you have referenced an address, brought it from memory to cache, then due to bringing another block and replacing that particular block, old block, if the old block is referenced again later, you can have a miss. Those type of misses are called conflict misses, right? So two different types of misses. One is cold misses, can't avoid them. First time an address is referenced, it's going to be missed anyway. The other type are conflict misses. Conflict misses depends on the structure of the cache and the pattern of memory access and all kinds of different things, right? So two different types of misses, something to note. Okay, so right, so we had 3 cold misses so far for this. No, actually one cold miss for each of these different cache implementations, right? We only had one access, right? So this is the status. After that miss, what happened was we brought the piece of missing data from the memory, right? The data at block address 0, data at block address 0 from memory, we brought here, right? Updated this entry. Data, the corresponding tag was 4 zeros, updated, and we set the valid bit to 1, right? Now we have a valid cache entry. After that miss happened, we fetch the missing block. Then in the two-way set associative cache, the same thing happened. Data from block address 0 from the memory was brought and stored here. Tag was 5 zeros, and we set the valid bit, right? We updated the entire entry. Then the fully associative cache, we brought and replaced this particular way, right? We wrote the data here, memory 0, data at block address 0, tag is 5 zeros, or sorry, 6 zeros, because we don't have an index field at all. Tag is 6 zeros, and we set the valid bit. Note that in this cache set, we started filling from the left hand side in. So it's our block placement algorithm or block placement hardware start searching from this side or left side from the set, and goes through the set to find the first invalid cache block and replace it. So finding the first invalid cache block will land us here. If you go back to the previous slide, previous status, so that was the first invalid block, and we replaced that in the fully associative structure. That was the first invalid block, so we put the new block there, right? Okay, I hope this is clear. So far this is the scoreboard. Direct mapped, one miss, two-way set associative, one miss, fully associative, one miss, right? All these misses are cold misses, right? Okay, now second memory address coming from the CPU, also a read, right? We are only looking at reads. So the offset we don't know, but the block address is 81000. So referring to the 8th block address in the memory, right? So what happens with the direct map cache now? Index is 00. Index is 00, right? So that particular entry, and do the tags match? Do we have a tag match? We don't, right? We don't have a tag match. And then why is that? Because the stored tag is 0 and the incoming address tag is 0010 or 2, right? The tag is 2 here, 0010. The stored tag is all 0. So the tag comparator will return a 0, and even though this entry is valid, you will have a miss here, right? And what about the two-way set associative cache? Will it be a hit or a miss? It's going to be a miss, right? Yeah, exactly, correct, very good. It's going to be a miss because the tags don't match, right? We don't have matching tag. There's only one valid entry in that set at index 0, right? At index 0, there is only one valid block, and the tag doesn't match for that, right? So it's going to be a miss in that, and it's also a cold miss because it's the first time that address is referenced by the CPU, right? And in the fully associative cache as well, it's going to be a miss because there's only one valid entry and the tag doesn't match for that. All the other entries are invalid, and even though the tags are also different, they are the validity status is also 0, right? So misses again for all three caches. Again, cold miss. It's a cold miss because the first time this address is referenced is this one, right? So the scoreboard stands the same, equal, 0 hits and 2 misses for all three different caches, different organizations. Now, right, so we have a repeated address. We have block address 0 referenced again, right? So only one after this address 8, we have block address 0 again, right? So temporal locality says recently accessed ones are likely to be accessed again. And here we go. We have 0 accessed again very quickly. What is the status going to be? Note that after the previous address, the missing block. We had misses in all three, and the missing block is brought into the cache. And in the direct mapped cache, we updated with the data from block address 8 from the memory, right? Block address 8. Block address 8 from memory, and the corresponding tag is 0010. So we updated that entry, right? If you noted, when we went from that address 8, when we completed that access, we updated this entry with the data from memory, block address 8 at memory, and the corresponding tag. Same with two-way set associative. We brought the data, but we had a separate an extra block space, extra space in that set, right? In this particular entry at index 0, the first invalid block was that, and we replaced it with the data from memory, new data. So we didn't have to throw out the old data. Like in the direct map implementation, we could keep the old data as well as save the new data, right? So we have a new valid entry with tag 0010 from memory 8. Then fully associative is the same. We had three different empty spaces. The first invalid or first empty one was this. So the cache controller saved the new missing block fetched from memory here and updated the tag, right? A 6-bit tag in this case, and set the valid bit. Now with the new address 0 again being referenced in direct mapped, go to index 00, it's valid, but the tag is not matching, right? Tag, incoming tag is 0, stored tag is 0010, number 2. So it's going to be a miss again for the direct map cache. And for the set associative, two-way set associative cache, index is 0. At that entry, do we have a matching tag? Yes, right? 00000. Two parallel tag comparisons will be done with these two stored tags, and one of them will be a match, right? 5 zeros. So one of them will be a match with the valid bit set. So you are going to have a hit in this way one of the of that particular set, right? One way of this particular set. The other is going to be an intermediate miss because the tag is not matching, but the final hit is coming due to the hit here in this way, right? So it is a hit here in the two-way set associative cache. Then the four-way set associative cache will have a hit because you can get a tag match in this way. In the first way here, you have 6 zeros, 6 zeros. There's a tag match and the valid bit is 1. For the other ways, the second way here, valid bit is 1 but tag doesn't match. The rest of them, valid bit is 0, so can't do anything, right? Okay. Now we have a hit in the four-way four-way set associative cache, or the fully associative in other words, right? So the scoreboard is 3 misses for direct mapped, 1 hit, 2 misses for the 2 associative caches, and the data has to be updated. So we had a miss in the direct map cache. Go to the memory, fetch the missing data from block address 0, put it there, update it, update the tag, and set the valid bit. Two-way set associative, we didn't have to do anything, it was a hit. Fully associative, again, was a hit, so we didn't have to do anything or replace any blocks, bring anything from the memory, right? Okay, next address. Add block address 6. Block address 6 comes direct map cache. What happens? What is going to happen? you are going to go to index 10, right? Index 10 is that. So that cache entry, it's going to be a miss because the entry is invalid. So we have a miss. Then two-way set associative cache, index is 0, only one bit is used. So index is 0, you go back to the same entry as used before, and we have two valid blocks there. But what about the tag? Tag incoming tag is 00011, and the stored tags are 5 zeros 00100. So none of the stored tags are matching. So the parallel comparators, both of them will return zeros for the intermediate hit status, and the final hit status will also be 0. So it's a miss here, right? So note that this is the first time this block address 6 is referenced, so it's going to be a miss. It's a cold miss, right? So cold miss in the direct map cache, cold miss in the two-way set associative cache, and it's going to be a cold miss for the fully associative cache as well, right? So let's update the status. 4 misses direct mapped, 3 misses for two-way set associative, 3 misses for fully associative, and the data is now being updated in the direct map. This is the cache entry that was referenced, and the data fetch from memory is put there, tag is updated, and valid bit is set. And in this particular set, right, when address 6 is referenced, you have to replace one of the two. Now the replacement policy comes into the picture because we have a miss and the entire set is full, right? That cache set is full at that index. So we have to replace one of the two blocks, and ideally the least recently used one has to be replaced. So the least recently used one is, so we have tags 000 and 00100 here, right? So those are the two tags from the two previous accesses, and the least recently used one is this, right? If we can ideally track the least recently used one, that is this 00100 block address 8, and that is the one that we will replace, assuming our cache controller can do the least recently used replacement policy. So even PLRU would have used that. First in, first out would have chosen the other block to be replaced, right? Note that different. First in, first out replacement policy would have chosen this because that was the first entry to come into the cache compared to the block address 8, right? So we replaced the block address 8, we evicted and replaced it with block address 6. Data from block address 6, tag and valid bit. And fully associative, in that cache entry, we had 2 more invalid sets, and the next one was filled using the data from the memory. Tag and valid bit was updated correspondingly. Next, we have block address 8 referenced again. What will happen? Direct mapped index 0, go to that entry, it is valid, tag is not matching, and we have yet another miss, right? So 5th miss for direct map. And note that this is a conflict miss. It's not a cold miss. This is the second time this address is being referenced, and it's a miss here. Just like what happened with this second reference of block address 0 for the direct map, it was a miss. It's a conflict miss. It's not a cold miss. Then in the two-way set associative, index is 0. We go to that entry. There are two ways. Do parallel tag comparison 00100. Then is anything matching? No, because we evicted that block address 8 from the cache just before, right? In the previous access, we replaced it. So it's going to be a miss. Again, a conflict miss because of a piece of data being evicted already, being replaced by something else, right? Conflict miss here. So conflict miss, what is going to be replaced now? With a miss, we have to fetch the missing data and replace. Which one is going to be replaced, assuming least recently used? Is it block address 6 or block address 0? If the replacement policy is least recently used, which block is going to be replaced? mem0 or mem6? This or that? Which one is the least recently used one? mem0, yes, exactly, mem0. So what about if we have first in first out replacement policy? Which one is going to be replaced then? First in first out, mem6 or mem0? Again mem0, right? This time it's the same block, right? So this time the first in first out will choose the same block as LRU. So ideal choice. In the previous occasion where replacement policy was needed, first in first out and least recently used, two different policies chose two different blocks to replace, right? So I hope you note these little differences, right? So in this case, mem0 will be evicted, this block will be evicted and replaced with block address 8. And what about the fully associative cache? Block address 8, parallel tag comparison, and we actually have a match, right? We have a tag match and a valid entry also. So we have a hit here, right? Tag match mem8 is here, right? Block address 8 data is here, it's valid, and we have a hit. So that's the second hit for the fully associative cache. So update the status. We had a hit here, nothing to be done. So 2 hits and 3 misses for fully associative, and 2-way set associative, 4th miss, and that particular block was replaced, right, with the new block mem8 block address 8 and direct mapped the 5th miss, and the data at that entry is now replaced with data from block address 8, right? So after 5 memory accesses, we had 3 different memory addresses or block addresses being referenced, and all 5 of these addresses or accesses were misses in the direct map cache. 3 of them were cold misses, 2 of them were conflict misses because of evicted data. Then 2-way set associative cache, we only had 1 conflict miss and 3 cold misses and 1 hit. Fully associative cache, there was no conflict misses so far, only 3 cold misses for the 3 addresses that were accessed first time, right? So as you can see, with the associativity, you get more hit, higher associativity, higher number of hits. The misses we have here in the fully associative are entirely cold misses, which can't be avoided at all, unless you have some magical way to know that these are the addresses that are being referenced by the program and bring them even before the program starts execution. So yeah, unavoidable cold misses. And with the increasing associativity, you get better and better hits, right? So less conflict misses. Conflict misses can be reduced with higher degrees of associativity, but with higher degrees of associativity, you introduce more complex hardware, right? So higher associativity, your hit rate is going to increase. the smileys are on. So hit rate is going to increase, which is a good thing. So you don't have to frown, right? So better hit rate, we like it, and hit latency is going to increase as well, as we saw with the implementation of the associativity concept in the cache. You have more hardware, more latencies, and hit latency is going to obviously increase, which we don't like, so you had to frown for that. So I will correct that before uploading slides. Okay, so higher associativity will improve your hit rate, but also at the cost of your hit latency, right? And what is not mentioned here is the power and chip hardware. The cost is also there, increasing with higher associativity. Okay, so right. So I think we have taken a bit more time than intended. Since only a few of you are here, I'll stop for today, and we'll complete this section tomorrow. So we'll have another lecture tomorrow at 9. We'll have about 1 hour, and we can complete this section there, right? Okay, so that's it for today. If you have any questions, of course, we can discuss. Otherwise, we can stop here.